Hello teachers, today I have a presentation about project of Central Processing Unit that we call CPU. And here is our team members including Mimi Siang, and Vinay, Ratha, Rosopi, and Ihir that we will present today. So here is our table content including introduction, circuit design and overview, key subcircuit, processing and control unit, development process, challenge and solution. Look at the introductions. Our projects focus on designing and implementing and functional CPU simulations using Circuitverse, an online digital logic platform. The CPU is designed to perform basic operations such as fetching, decoding, and execute instructions. It can also handle arithmetic operations, data transfer, and control instructions. To make the designs more realistic, we include features such as pipelining, memory management, and interrupt handling. The main goal of this project is to apply sequential logic concept and use digital components like logic gate, flip-flop, multiplexer, and decoder to build a work CPU. So these projects help us understand how computer hardware works and connects theory with practical implementation. This slide presents the overall architectures of our CPU design. First, the CPU executes instructions through several interconnected subsystems. Instructions are fetched from memory and sent to the decode. Next, the decode generates a controlled signal while the arithmetic logic unit or ALU performs arithmetic and logical operations such as addition, subtraction, and comparisons. Registers are used to temporarily store data during processing. Finally, the control unit coordinates all system operations, ensure that data flow correctly and instructions are executed efficiently.
Now I will explain the key subcircuits of our CPU. The 8-bit register temporarily stores data during processing. The instruction register or I/O holds the current instruction after it is fetched from memory. The program counter stores the address of the next instruction to be executed. The opcode decoder identifies the operation, specify the instructions such as add or load. The sequencer and command decoder generates the control signals needed to execute each instruction in the correct order. Finally, the real-time sequencer synchronizes all CPU operations with the system clock to ensure accurate execution. Next are the processing and control units. The ALU or arithmetic logic unit performs arithmetic and logical operation. The adder module carries out binary addition and supports arithmetic calculations, and the multiplexer select the correct data input before it is processed by the CPU. The register selection decoder determines which register should be accessed based on the instruction. Finally, the control unit acts as the brain of the CPU by generating control signals and coordinating all components to execute instruction correctly.
Now I will explain the development process of our CPU project. To build our CPU, we follow a step-by-step approach to make the designs more organized and easier to test. First, we created truth tables for the control signal. These truth tables help us determine how each instruction should control different parts of the CPU, ensuring every component receives the correct signal during executions. Next, we build the opcode decoder. Its job is to read the instructions opcode and identify which operations the CPU needs to perform, such as addition, subtractions, and data transfer. After that, we developed the control logic and execution sequencer. These components generate the control signals and ensures that every instruction follows the correct sequence of stages, including fetch, decode, and execute. Then we implement the arithmetic logic unit, or we call it ALU, which perform all arithmetic operations such as additions and subtractions, as well as logic operations like AND or NOT. Finally, after testing each modulo individually, we integrated all the components into a complete CPU systems in Circuitverse. We verified that the modulos communicated correctly and that CPU could successfully execute instructions from beginnings to ends. By following these instructions development process, we were able to build a functional CPU while reducing design errors and making debugging much more manageable. Thank you.
Let's talk about the most important part of our project, the challenge we faced while building the CPU. We faced four main problems. First, we faced state instability. The CPU pads don't work together at the same time. Signal arrive too early or too late, causing bug in our memory. To fix this, we make clear truth table. We match every signal to the system clock cycle so everything moves together perfectly. Second, we struggle with complex logic. As we add features, our math formula became too big. Simplifying them by hand is confusing and lead to mistakes. To solve this, we use Kano map or K-map. This visual tool helps us simplify our math quickly and use fewer logic gates. Third is a clutter wiring. In circuitry, many wires look like a messy spider web. Finding mistake is very hard. So we change our strategy. We build and test each small part like the register or the ALU separately. Once a part works, we connect it and label the wire clearly. Finally, we have a knowledge gap. Building a CPU is much harder than our basic classes. We solve this with teamwork. We share the research and teach each other. When one classmate learns how a part works, we explain it to the rest of the team. This challenge don't stop us. They teach us how real engineers solve problems. That's all. Thank you.
I am Hanta. I'm from Group CPU Team 6. Today, I will explain how all the components in this circuit work together to form the control unit of our 8-bit CPU. The operation begins with the clock signal, which synchronizes the entire CPU. Every clock pull move the CPU to the next execution step. First, the sequencer receives the clock and generates timing signals such as S1 and S0, S1, S2, S3, and S4. This time signal determines when each action should happen during the instruction cycle. At the same time, instruction address register or program counter store the address of the next instruction. This address is sent through the address multiplexer to RAM, allowing the CPU to fetch the required instruction. The instruction stored in RAM is then sent to the opcode decoder. Here, the decoder examines the opcode and determines which operation the CPU must perform, such as load, store, or add. However, knowing what operation to perform is not enough. The CPU also needs to know when to perform it. Therefore, the output from the output decoder are combined with timing signal from the sequencer inside the circuit command. Together, they generate a control signal for the entire CPU. These control signals are then distributed to different components. The register decoder The registered coder activates the correct register based on instruction, ensuring that only one register is enabled at a time. This prevents data conflict on the shared bus. When an add instruction is executed, the addition multiplier yeah, that when an add instruction is executed, the addition multiplier select the correct operand and send it to the ALU. The ALU perform the arithmetic operation and produce the result. Finally, the control signal enables the destination register, so the ALU result is written back and stored. At this point, the instruction has been complete, and the program counter advances to the next instruction. The entire process repeats for every instruction in the program. In summary, the control unit acts as the coordinator of the CPU. The resequencer controls the timing. The opcode decoder determines the operation. The sequencer command generates the control signal. The register decoder selects the correct register, and the additional processor routes data to the ALU. By working together, these components ensure that every instruction is executed in the correct order and at the correct time.